So we understood about this LC oscillator in which a capacitor is disturbed by adding some charge on this. Similarly, as we move this mass from its mean position to one side of the mean position, so this is disturbed and it will try to oscillate in simple harmonic motion. Similarly, this capacitor is disturbed by providing charge on this capacitor, then connected to an inductance. Once this inductance is connected, the current start flowing in this circuit and this inductance started becoming magnetized. Once it is fully magnetized at maximum current, the charge on the capacitor is now 0. So electrical energy on this capacitor is 0. All the energy has now been converted to magnetic energy. Now this inductor is starting provide the current to this capacitor. That means it started charging this capacitor. After some time, the inductor has no magnetism inside and capacitor is fully charged. Now this cycle will keep on repeating again and again. So this works like the mechanical vibration of a mechanical oscillator. Only two things we have to consider. First thing, this inductance must have some resistance, because there is no inductance which has zero resistance. In that case, these oscillations will slowly die out, as in case of damping in the mechanical oscillator. But even if we consider there is no resistance in this inductor, the electromagnetic radiation coming out of this circuit will result in loss of energy and ultimately the oscillations will die out. After that, we saw how these two phenomena compare each other and equivalence between these two phenomena, and these are the equations, and we simply change some of the terms, some of the parameters for mechanical oscillations to electrical oscillations, and we found very similar equation, exactly same equation for LC oscillations. Now let us do this example 7.11. So example 7.11 show that in the free oscillations of an LC circuit, the sum of energies stored in capacitor and the inductor is constant in time. So this is very similar question. In class 11th, we have showed that kinetic energy and potential energy, sum of kinetic and potential energy of a simple harmonic oscillator is constant. So this we had shown in class 11th. Now we have to show that electrical energy and this magnetic energy in an LC oscillator is constant. This we have to show. So let us show how to prove this problem. So let us see. So first of all, let Q be the initial charge on the capacitor. So we have assumed that Q0 is the charge on the capacitor. Up to this value we have charged the capacitor. Let the charge capacitor to be connected to an inductor of inductance L. So after that, once we have charged, we connected this to an inductor of inductance L. As you have studied in section 7.8, this LC circuit will sustain an oscillation with frequency. So what will happen? So this circuit will start oscillating with a frequency omega is equal to 1 upon under root LC, and this omega is equal to 2 pi nu. At any instant t, the charge Q on the capacitor and I current are given by. So now we have moved from initial condition. Now t is not 0. After some time, we are talking about after some time. What happens after some time? Now this charge has started decaying. Charge is started decaying, and we have written function of this charge in cos, because we took the maximum charge. So charge is decaying, so that's why it is a cos function. And current is 0 initially, it is increasing, that's why current is a sine function. Also we can get this equation by simply differentiating the charge. If we differentiate the charge with respect to time, so what we get? Charge is Q0, this is maximum charge, very similar to amplitude, and this is a cos function because it is decaying. So what do we get to the current, we simply differentiate this dq by dt, and this dq by dt is q0. Cos omega is minus sin omega, and this omega comes out once again, so q0 omega sin omega t. So in this way we get the equations for charge and current in the system. So now this gives the charge on the capacitor at any given time, and this gives the equation for current in the circuit at any given time. Energy stored in the capacitor. Now let us calculate what is the energy stored in the capacitor. So first we are assuming that at t time we are calculating what is the energy stored in the capacitor. So this must be electrical energy, and what is the formula? Formula is half CV square, and from this Q is equal to CV, we converted this formula to 1 by 2. Since this V is equal to Q by C, so we have put this value. So V square is Q square by C square, and 1 C was already there. So 1 power is gone, so we get Q square by C. So half Q square by C. This is our electrical energy. Now let us put the value of Q. So this is 2C. This is the capacitance of the capacitor. What was Q? Q is Q0 cos omega t. So what we get? Q0 square cos square omega t. So this is our electrical energy. After that, we have to calculate what is the energy stored in the inductor at time t. So in inductor we have stored magnetic energy, sometimes showed by UB. Here they have shown by UM. Again this is a kind of magnetic energy. So this magnetic energy is half Li square. So this is half, L is L. Let us put the value of I square. So I is minus Q0 omega sin square omega t. So when we square, so this minus sign goes out. So Q square, this omega square sin square omega t. Now let us use our relation between this frequency, capacitance and reactance. So from this we can write this omega square L. So we know this omega is equal to 1 by under root LC. So let us square. So omega square is equal to 1 by LC, and this omega square L comes out to be 1 by C. This is 1 by C. So let us put the value here. So this omega square L is 1 by C. So what we get? 1 by 2. 1 by 2. This omega square L is equal to C. 1 by C. And this is now Q0 square and sin square omega t. So this is the equation. So Q0 square upon 2C sin square omega t. How do we get? We use this relation between frequency and LC. Now let us sum these energy. So first let me clear this screen. So what we have? We have two energy. First is the electrical energy. Electrical energy is Q0 square upon 2C cos square omega t. And second is the magnetic energy UM. This is Q0 square upon 2C sin square omega t. Now let us sum these energy. So UE plus UM. So first we take this common, Q0 square upon 2C, that is common, and this is, from this we get cos square omega t, from this we get sin square omega t. Again let us use the identity, cos square theta plus sin square theta is equal to 1. So whatever their values are, whether theta is 0 degree, 90 degree, whatever the value of theta, this identity always remains 1. So this whole things, since the angle for both of them is omega t, so this becomes 1. So what we get? Q0 square upon 2C. Here what we can see? We can see that we have calculated this energy at any given time, and we got this number Q0 square upon 2C. So initial charge Q0 is not changing, square of that is also a constant. 2 is also a constant. This C is again a constant. So capacitance is constant, Q0 is constant, 2 is constant. Since all of them are constant at any given time, so we can say the combined energy of the circuit is a constant. This sum is constant in time as Q0 and C both are time independent. None of them is changing with time, that's why this is a constant. Note that it is equal to the initial energy of the capacitor. Why it is so? So think about it, why it is equal to the initial energy of the capacitor. So here we have seen that in LC oscillations the sum of electrical and magnetic energy remains constant as the sum of kinetic and potential energy in a mechanical oscillator remains constant.